Swayam Prabha. Digital India. Educated India.
Welcome back. Welcome to the course Mechanics of Solids. So in the last lecture we were discussing about the laws of mechanics and the steps involved to analyze any mechanical system in the way whatever we generally see in the universe, right? And then basically we talked about force, how to calculate force, how to quantify force, and what are the consequences of forces. So those things we have seen, and then we discussed about moment of a force with respect to a particular point in the space, right? So those things we have covered in the last lecture, and now we are in this particular lecture we are going to establish some laws, whatever we have discussed in the last lecture, that every mechanical system will follow some law. I mean, it cannot violate the laws of mechanics. Okay, so those laws we are going to explore in this particular lecture. So basically, the first thing is that we'll be talking about the equilibrium conditions. Okay, so this is one law. So if I say my mechanical system or any system is under equilibrium, then what do we understand by that? Okay, so let's write down the statement: if a resultant force acting on a particle is 0, then the particle will not be having any acceleration. And this condition is called equilibrium condition. So what do you understand by that? If a resultant force, suppose you are considering one system and that system is under the action of different forces, okay, not only a single force, it can have a multiple number of forces are acting on that particular system. So we will be having some resultant force, right? So as you know that, because as I told you in the last lecture, that force is a vector interaction. So vectorially you can get the resultant. So if a resultant force acting on a particle, not even a whole system, even if you consider a particle in that particular system, then so resultant force acting on a particle is 0. Okay, the resultant force is 0. Then the particle will not be having any acceleration. So resultant force is 0. So therefore the particle will not be having any acceleration, and this condition is known as equilibrium condition. Now what exactly we understand from that? So let's talk about, or let's write down those statements, and one by one we will discuss those things in the coming hour. Okay, a particle in equilibrium is one that is stationary or that moves uniformly relative to an inertial reference. Okay? So, a particle in equilibrium, so when I am talking about the equilibrium condition for a particle, so a particle in equilibrium is one that is stationary, either stationary or that moves uniformly relative to an inertial reference. So, as I told you from this statement, it is clearly mentioned here that the particle will not be experiencing or will not be having any acceleration. So, it can happen only in two situations, either the particle is stationary or the particle moves with the uniform velocity or uniform relative, say, inertial uniformly with respect to some inertial reference, right. So, under these two situations, basically you will not be having any acceleration. So, a body, now we are talking about a body is in equilibrium if all the particles that may be considered to comprise the body are in equilibrium. So, initially we talked about a particle. The particle is in equilibrium. So, particle is in equilibrium when either you have the particle is stationary or you have the particle which is moving uniformly. Okay. Now, if I say a body, now we consider a tiny say a particle. Now we are talking about a body, whole body. A body is in equilibrium if all the particles, okay, that may be considered to comprise the body, which will form the body, okay, are in equilibrium. So, basically what I mean to say, that if I say a body is in equilibrium, that means each and every particle in that body will be in equilibrium. Okay. Now, what are the laws of equilibrium? So, those things we are going to discuss now. So, now basically if you look at the general equations of equilibrium, how we can establish the equations of equilibrium. So, the necessary and sufficient conditions of equilibrium is that the summation of all the forces, that means the resultant force as well as the resultant moments. When I am talking about the force, that means the force which are externally applied on the body. So, if you look at this figure, basically in this figure you have the whole body, okay. So, this is your whole body, this is your body. Now, this body is under the action of different external forces F1, F2 up to Fn, and due to that external force, application of the external force, you are getting the internal forces which are getting developed here, right. So, these are all internal forces, right. So, now what I am saying when I am going to establish the equations of equilibrium, at the time we are talking that the resultant forces, that means resultant forces of externally applied force, okay. So, resultant forces and resultant moments, that is becoming 0, then only you will be getting the equilibrium condition, okay. So, what I can write now, so what I can write now, the necessary conditions for a rigid body to be in equilibrium are that the resultant force Fr and the resultant moment Mr for any point A, B, 0 vectors. Okay. So, this is the law. This is the law of your equilibrium condition, that the necessary conditions for a rigid body, we are talking about the rigid body. Okay. So, for a rigid body to be in equilibrium are that the resultant force, that is Fr, and the resultant moment caused by that those externally applied forces, okay, for any point A. So, any point in that space, and we have seen in the last lecture that how we can calculate the moment with respect to some fixed point. Okay. So, be 0 vectors. So, resultant force and resultant moment must be a 0 vector. Okay. Now, mathematically how we can express that? So, mathematically I can express this, so that gives me summation of all forces equal to 0 and resultant moment is 0, that implies that summation of the moments of externally applied forces, okay, in that way you can calculate, plus you may have some concentrated moments acting on the body, right. So, this is the moment due to the externally applied forces, and this is the moment which are concentrated moments acting on that particular body. So, summation of these things must be 0. So, mathematically I can express like this. Okay. Now, if I consider a body, let's talk about, so I mean, are these two equations, are these two relations are sufficient? So, that is my question. So, let's see, let's talk about that. Let me draw a figure, small figure. Suppose this is one body. Okay. So, you have different externally applied forces. Only forces I am showing. So, if you understand this concept for the forces, for the moments, things will be pretty similar. Okay. So, these are few externally applied forces. Okay. And you are considering one point, say A, and you want to find out the moment of these forces about point A. Okay. So, you need to know the displacement vectors. Okay. So, these are all your displacement vectors, say R2, R1, R2, R3 and R4. These are all your displacement vectors, okay, R1, R2, R3 and R4. So, now if I want to establish these relations, that is the equilibrium conditions, what I can write? I can simply write F1, because resultant force must be a 0 vector, okay. So, summation of all the forces must be 0. So, F1 plus F2 plus F3 plus F4 equal to 0. So, that is my say equation 1, okay. Now, similarly my resultant moment is also 0 for the equilibrium condition. So, I can write R1 cross F1 plus R2 cross F2 plus R3 cross F3 plus R4 cross F4 must be 0, say equation 2. Is there any doubt? I hope there is not. Okay, so we are just following these equations, nothing else for this body. Okay. Now I am considering another point here. So this point is say B, and the displacement vector between B and A is say rho. Okay. So I am considering another point B, and let's see that if I choose another point, whether my equilibrium condition will be different or not. So then we can say these are two my basic equations for your equilibrium condition, right? That in that way we can say that. Okay. So if I consider another point, say B, okay, in this body, and the displacement vector between B and A is a rho, then I can simply write for the new point B, I can simply write down that R1 B. What is R1B? R1B is the displacement vector for force F1 from point B. Okay? That means that is the displacement vector to the point where F1 is acting, okay, from point B. So that is defined by R1B. So R1B from your vectorial say equation or the vectorial say rules, you can write down R1B is simply equal to displacement vector rho plus R1, isn't it? What is R1? R1 is the displacement vector between the point where F1 is acting and point A. So this is the displacement vector between A and B. So in that way I can get the displacement vector from point P, the newly chosen point B. Similarly, I can write R2B is equal to rho plus R2, okay, and so on. Okay. So now what I can write? So therefore, if I try to exploit the equilibrium condition, that is the moment equilibrium, like the resultant moment with respect to B is 0. As I told you, the resultant moment must be 0, no matter what point we are choosing. Now we are going to prove that if we choose different points, it will be remaining same. That is my actually the objective. Okay. So now if I choose point B and if I take the moment equilibrium, that is your summation of MR with respect to point B is 0, then I can simply write R1B into cross F1. So that directly I can write R1 plus rho cross F1 plus R2 rho cross F2 plus R3 cross F3 plus R4 cross F4 must be 0. That is also equally valid, because instead of choosing A, because nobody is telling me that which point has to be chosen for taking the moment equilibrium. So, I am choosing some other point, say B. So, then the equation will be transformed like that, right? Equation will be getting changed, and that will take the form like this. Okay. So, now if I simplify this, I can get simply R1 cross F1. I mean, by following the distributive law of your vector, I can simply write R2 cross F2 plus R3 cross F3 plus R4 cross F4 plus rho cross F1 plus F2 plus F3 plus F4 equal to 0. Can I write? Yes, of course we can write, right. Now, if you look at this equation, this part is already 0, because we are talking about the equilibrium condition, and that is already established, that is the resultant force must be a 0 vector. So, this is already 0. So, what is left out? This is left out. Now, if I say this is my equation 3, then equation 3 is nothing but your equation 2. If you go back to your lecture, so equation 3 ultimately or eventually becomes equation 2, because this part is of course 0. Okay? So, now what I can write from this discussion, that, so I can write there are only two independent vector equations of equilibrium for any single free body. This is very, very important. So, there are only two independent vector equations. What are those? Summation of Fi equal to 0, summation of Mi equal to 0, right. That means Fr, that is the resultant force, is 0, resultant moment is 0. These are two basic equations of equilibrium for any single free body, and rest of the equations, whatever you want to develop, all those things ultimately will follow these two equations, and that already we have seen. See, if it is not following, if this rule is not followed, okay, then what you should get different equations. So, equation 3 should be different than equation 2, that you are not getting. So, that insists that you are only getting two independent equations of equilibrium. Okay. So, now few consequences, few say discussion may come out from this say topic, that, so few discussions may come out from this topic, that we can use equations 2 and 3 instead of equations 1 and 2, right. So what was there in equation 1? That is the resultant force is 0. What was there in equation 2? That summation of moment with respect to point A was 0, right. What was there in equation 3? Summation of moments with respect to point B was 0. Now, these, as I told you, these are two your basic equations, independent equations, equation 1 and equation 2. One is force balance, another one is the moment balance with respect to point A. Now, instead of that, instead of taking the force balance, that is the resultant force is 0, instead of taking that, I can choose these two equations. That means both equations are talking about the moment balance. That means I am talking about the summation of moment with respect to point A is 0 and summation of moments with respect to point B is 0. I can use those two equations to solve our equilibrium problem. Okay, that we can do. There is no problem in that. So, I mean, in the subsequent lectures, when we will be talking about different structures and different kind of configurations, you will see that as per your convenience, basically sometimes you use this set, that means only moment balance. You are taking moments at different locations and you are finding out the moment balance, or you can get the combination of moment balance as well as the force balance, right. So, there is no problem in that. Now, as you have seen that what we are talking about the resultant force must be 0 and resultant moments must be 0. Now, for any force or any moment if you consider in the space, and if you consider a mutually perpendicular coordinate system x, y, z, right, mutually perpendicular coordinate system x, y, z, then any force can be resolved in the space. If you consider any force, that force can be resolved in this x, y, z coordinate direction. Similarly, the moment can be resolved in x, y, z coordinate direction, right. Like if you have the force F can be decomposed or resolved along x axis Fx, along y axis Fy, and along z axis Fz. Similarly, the moment Mx, My, Mz. So, most of the times we are not talking, or we are not taking this thing in calculation, that is the force, the whatever force is there, we are not taking the summation of that particular force, or for our convenience sometimes what we do, that we resolve all the forces along the mutually perpendicular coordinate system x, y, z, and similarly the moment we also resolve, and then we take the, or we exploit the equilibrium condition. So, for that what we can write, so when you resolve the forces in x, y, z coordinate system, then you can simply write summation of Fx equal to 0, summation of Fy equal to 0, and summation of Fz equal to 0. So, instead of taking the F in the space, you are just resolving this force in x, y, z coordinate system, and then you are taking the equilibrium along individual coordinate direction Fx, Fy, Fz. Similarly, I can write summation of Mx equal to 0, summation of My equal to 0, and summation of Mz equal to 0. So, that will be convenient to use for any kind of system. Okay. So, and later on you will appreciate that we will be frequently using these relations, okay, to solve our system which is under equilibrium. So, I will stop here today. So, in the next lecture we will be talking about the free body diagrams and different force configurations. Thank you very much.